Hey everybody, welcome. So this video is part of our Introduction to AI Concepts video. And what we're going to talk about today is artificial neural networks or neural networks. And one of the things that's really important in artificial intelligence, and this is how I decide if a project is actually an AI project or a data science project, it's does the project include a neural network? So up until 2019, 2020, I would never tell anybody that I worked in AI. I only worked in data science. And the difference between being a data scientist and an AI engineer is this concept of neural networks. So what I want to do today is I want to give you the background you need to know about neural networks and how they work and a lot of the vocabulary that goes into neural networks. Because one of the things about working in AI is it's buzzword bingo. There's just so many terms, so many concepts. And even though I don't really think it's all that important for you as an AI engineer in 2025 or beyond to actually understand neural networks and be able to work with them yourselves, you do need to know the basic concepts because when people are talking about AI, at some point they're going to be using the terms that come from neural network. Now, a neural network is not new. It came out initially, Frank Rosenblatt in 1957 came up with the first artificial neural network called a multi-layer perceptron. And his idea was he wanted to have a series of cameras laid out that he could look at something and tell what it is. And in order to do that, he basically modeled how the brain works in a very rudimentary way. So don't jump in my comments about how this isn't how the brain works, because in a very basic way it is. It's just organized differently. So inside your brain you have two things. You have neurons and you have synapses. Neurons are little points of electricity, and that can be from zero, no electricity in the neuron, to the maximum amount that the neuron can hold. Let's just call that 1. So it's a real number between 0 or 1 if we're creating a function out of it. But inside your brain you have this little dot of electricity, and you have 100 trillion of these little dots of electricity. Now these little dots of electricity, and let me bring up a picture here, are connected to each other. So in your brain, each synapse or each neuron is attached to the other neurons through something called a synapse. So the synapse is actually a resistor between the one neuron and the next neuron at the next layer. And that's where the term layer comes out. So if you look at this image, you see that there's a bunch of layers. So we have our input layer. And in the case of the multi-layer perceptron, he had, let's say you were going to go 16 by 16. And you were looking, and that would be a 16 by 16 image. Now think about how many pixels an image has today, and think about in 1957, 256 cameras. You have them lined up. And then when they look at the image on the wall, each of those input layers or each of those input devices passes in a number as to what it sees. So if there's nothing, it's 0. So if it's white, if the thing that camera is capturing is white, it's 0. And if it's pitch black throughout the entire detector, it's 1. So you have from 0 to 1. And then that would be called the weights. So when we talk about in biology neurons and synapses, in computer science and AI, we're talking about weights and biases. So your neuron is the weight, the synapse is the bias. So this input device takes in a 0 to 1 number based on whether it's white 0, black 1. Then it takes that and it passes it to the next layer. And then the next layer, and keep in mind, so each of the 256 cameras passes in a number to the next layer. And then the next layer runs a calculation on it for all of the elements of its layer, and then passes it to the next layer. That's why it's called multi-layer perceptron. So you have 3 types of layers. You have your input layer, which is the detector, your hidden layer, which is where the real work is done, and then your output layer, which is the results. Now, in the most basic, let's say you're creating a device that it's going to determine if a number it sees is between 0 to 9. It would actually then have 10 output layers. And which of the 10 has the highest voltage is the number that it detected. So it looks at the screen, it sees the number from 0 to 9, then it passes in the 256 dots, and then based on the resistance from one layer to the next, when it gets to that final layer, that output layer, it can tell you, is that between a 0, is that a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, based on how strong the electricity is. So let's say you put in the number 9, that ninth output layer, if it's 100% positive that it is a 9, it is going to come back with a 1. So what you're doing when you're training a neural network is you're taking the neurons or the weights in these hidden layers, and you're determining what the weight should be and what the bias should be. So you're determining at every layer, you're determining every weight, how strong it should be from 0 to 9.999, and then every connection to the next layer, how much resistance does it give? 0 meaning it gives no resistance, or 0.999, which means there's so much resistance that value from the first neuron. I keep trying to use neurons. I got to keep calling them weights. The weight, the neuron in the hidden layer, if you got 100% resistance, it's not being passed. So notice on this document, I've got 3 detectors, which are the input layer. Now, somebody brought this to my attention recently, and I 100% agree. These are not neurons, okay? They're basically, it's an input layer. After the input layer, the rest of these all have values to them. They have weights, but the first layer does not. So the first layer takes in what it sees, and it assigns it its initial value, its detector value from 0 to 0.9999. Then it passes it to the hidden layer, and then it goes all the way through to the output layers. Now, the way this is trained is intriguing, and that's where you hear terms like back propagation and then labeled training. So what they would do, we actually, there's a project that we'll create. A reminder, sign up at Oasis AI Learning, because the project that goes with this will be there. It's free, no reason not to do it. So what we do is we take the input data and you say, hey, and the neural network starts by just guessing. So it randomly assigns weights and biases for every synapse and every neuron through the system. So it just guesses, and it randomly says, well, this is where we're going to start. This is our starting point. Then you pass in a 1, and it guesses an answer. That answer, let's say that answer is, it guesses a 6. And you say, nope, I passed you a 1, you came up with a 6. So then it recalculates all the weights and the biases. It uses a term from calculus called gradient descent, which is how much it moves. So it takes all of these weights and moves them by a little bit, takes all of these biases, moves them by a little bit, then you pass in another number. You don't keep passing the same number all the time, because then what it's just going to be doing is memorizing. Then you pass in, let's say you pass in a 4, and it guesses 6. And you say, nope, it's not a 4, it's a 6. So it changes the weights and the biases a little bit, and then you do it again. Now you just keep doing it. You pass thousands, tens of thousands, hundreds of thousands of these images in, and it keeps guessing the answer. Now, over time, as these weights and biases of the neural network get calculated and refined, it starts getting really good. So in your data science project that you would do or that you're going to do, you start out with, let's say, 100,000 images of numbers. You take 10% of those, you put them off to the side, because that's how you're going to test to see how well you trained your neural network. Then what you're going to do is you are going to pass in these numbers and you're going to let it start guessing. Now, by the time you get through, let's say, the 90,000 images, it's probably getting pretty good. Okay, you're putting in a 6, it's seeing a 6. You're putting in a 1, it's seeing a 1. Now, keep in mind, this is a little bit more complicated because of fonts. Now, back in the old days, if you only had one font, and it was the typewriter font, a 1 always looks like a 1. But nowadays, a 1 might look like the letter L. So it's a lot more complicated. So as the neural network gets trained, these weights and biases get more defined, and it gets to the point where it can answer the question correctly. Now, this gets big really, really fast, because every time we're talking about having 256 inputs because we're going 16 by 16. Think about how big a 20 megapixel image is. Now, you're going to be doing the same thing. You're going to be figuring out the weights and the biases, but instead of having 256 inputs that you're using, you have 100 million inputs. And those inputs are tied to all of the different layers. So you're taking this mathematical equation and you're starting by guessing, and then over time it's getting better and better. Now, this is why neural networks require GPUs. Think about how many things you're recalculating when you're training this neural network. So I've got 256 in, and let's say I've got 4 layers, okay? You're actually going through that whole tree, recalculating all weights on all layers every time you guess again, okay? Now, a CPU is very limited on the amount of floating point mathematics it can do. But a GPU runs these mathematical equations in parallel really, really fast. So when you think of like the number of CUDA cores, like the number of CUDA cores in NVIDIA RTX 4090 is about 16,000 cores, which means it can be doing 16,000 of these neural network calculations at the same time. If you had a 10-core GPU, or CPU, it could only do 10 at a time. The massive parallel processing requirement that is necessary to do all these calculations. Now, keep in mind, these calculations are fairly simple and straightforward. We're not doing a lot here. We're doing a floating point operation. You're increasing one number, you're decreasing another number, and then you're running through and running this calculation. That's, from a CPU standpoint, that's way more than your CPU is going to be able to handle, because at best it could do, if you've got 10 cores, it can do 10 of these calculations at once. Now, when we get to something where we're looking at, let's say we're looking at medical imaging, and we're taking the input is 10 megapixels. So it's 10 million pixels, 10 million dots on your input layer. And then your first hidden layer might have 10 million dots again, or neurons again. And so all of that recalculation that you're doing in your neural network is a ton of resources. So when we think of neural networks, we're thinking of the internal structure. We're thinking about what is happening inside of your AI. Now, this training is taking a bunch of neural networks. And so an LLM takes a bunch of neural networks, and each neural network inside of the LLM is doing a different thing. And that's why you'll hear a lot of people refer to them as perceptrons. Okay, a perceptron is a simple feed-forward neural network. And everything that I've been describing up until now represents a feed-forward neural network. So in this case, in this image that I have up on the screen, the X, Y, and Z are coming in, and you're only going in one direction. So you're going from the input layer to the first hidden layer to the second hidden layer, and then that is giving you the output in the output layer. So that's feed forward. So the idea is you're putting it in one end and it's coming out on another end. There's another type of neural network called a convolutional neural network, and that's good for image recognition. What the layers are doing in a CNN, in a convolutional neural network, is different. Okay, it's actually doing a thing called filtering, where it's looking for specific patterns inside of the pixels, because it can't look at, if you're pushing in a 10 megapixel, a 10 million pixel image, it can't look at all 10 million images at a time. So it's going to break it up into 3x3 squares, and it's going to process them as the 3x3 squares, and then it's going to have another layer that groups the 3x3s together, and it runs through the image looking for patterns that, if you're looking to see if the person has aortic aneurysm on their CT scan, it knows what one of those looks like. And in this case, the neural network is looking to say, hey, does this image have one of these somewhere in it? Now, the reason I'm talking about neural networks is this is where training occurs. The concept of training, when you're training anything, you're training neural networks. So you're in the most basic, the supervised training that we were talking about, this works with labeled data. It's not, the AI is not figuring out anything on its own. What it's doing is you're giving it a thing, and then you're telling the system what the thing is. So that as it runs through, if I say I'm looking, this is a horse, and it's actually a cow, you've got these labeled data where you're telling the trainer, the LLM, or the neural network trainer, you're telling the trainer what the answer should be, and if the trainer gets the answer wrong, it recalculates. So in the project for this, what we do is the most basic project is something called MNIST. And MNIST is it's a data set of these numbers, and there's 16 by 16 numbers. And you take these numbers, and there's some this is one of your first college courses with neural networks, is to take the MNIST data set and to just run it through and train your first neural network to look at something and tell us what the output is. So I think that's all I'm going to cover for on neural networks. But before I get too far, let's just talk about what a couple of the key concepts that it's important that you understand at the end of watching this video. So a neural network consists of weights and biases. It's a mathematical, or it's a computer representation of the basic operation of your brain, which is neurons and synapses. And so the same way that your brain can look at a number 1 and say that's a number 1, that's because your brain has had its weights and biases, or your neurons and synapses, adjusted in such a way that it knows that that is what a number 1 looks like. So you've got your input layers, your hidden layers. So one concept that you need is the input layer. That is the data that's coming in. Your hidden layers are where all the magic happens, and then your output layers is how it is representing the results. So in my 0 through 9 concept, we'd have 10 neurons in the output layer, and whichever one has the highest value, the closest to 1, that is the number that we saw. Training is done through a concept of backpropagation. And the way backpropagation works is it works backwards. So let's say we put in our X, Y, and Z, and we have our labeled data. So we put in our X, Y, and Z, and it goes to the first hidden layer, the second hidden layer, then it outputs something. Now it outputs something wrong. So then what back propagation does is it works backwards. It's concept of, this is where gradient descent comes from. So this is a linear algebra and calculus gradient descent problem. It is then going to work backwards and recalculate the weights and biases backwards. Then it's going to try it again. Then it's going to say, nope, that's not right either. And then it's going to work backwards again. Now, what you're trying to avoid when you're training a neural network is you're trying to avoid something called overtraining. Now, what overtraining is it's basic memorization. That's when you've trained it so much or overtrained it that at the end, it's memorized the results. So you put in, let's say, 50,000 images, and it's now just memorized those images. And that's where overtraining comes in. And it's also sometimes it's called overfitting. So training is an art as much as it is a science. The idea of training your neural network is you want a neural network that's right most of the time, but you didn't overtrain it so that it's memorized things. So one thing of, let's say, one place where overtraining goes bad is, let's say you train it so much on, let's say, the typewriter font or the Arial font or the Times New Roman font. Now somebody comes in with my terrible handwriting and they write a 1. Or, the physicians I work with, if you've ever seen a physician's signature, try detecting things from that. If you overtrain and you memorize the input data so intensely, your model is never, it's always going to be guessing. It's actually, overtraining actually makes the results of your model less accurate than training to a certain amount. So again, we've got our input layers, we've got our hidden layers, we've got our output layers. They're trained using back propagation. Okay, so at this point we have talked about the basics of what a neural network is. So now let's take a couple minutes and talk about the different types of neural networks. So the one that we have talked about initially with that diagram is called a feed-forward neural network. That's because the process moves from the beginning through the end, feeding the data forward from the input layers through the hidden layers all the way out to the output layer. So it is possible to have something that is a single layer, but that's not the most normal thing. In most cases, we're talking about a multi-layer neural network. The second type we want to talk about is one that I've talked about a little bit. I just kind of threw it out there, which is called the convolutional neural network. And again, a convolutional neural network learns directly from the data, which means there's really no manual feature extraction. But it's very, very useful. CNNs are very useful in finding patterns in images. So, is that a car? CNNs are used in self-driving cars kind of religiously. And I know they are trying to go to some other things, but knowing that that thing on the side of the road is a fire hydrant and not a 2-year-old is done by a CNN. So in a convolutional neural network, it consists of an input layer and an output layer and a bunch of hidden layers. But the hidden layers are a series of what's called the convolutional layers. And they convolute with multiplication or other dot products to determine in groups as it's moving through, it's determining what it's seeing inside of the image that you gave to it. So that's your convolutional neural network, and that is used for image recognition. Now, just as a caveat here, everything that I'm talking about can be done with a GPT, which is a generalized predictive transformer. And there's a big push in the world to do everything with GPTs. And that is possible. But GPTs are not necessarily the most cost-effective when you're talking about what kind of neural network you want to use. So for image recognition or for looking for objects in an image or in a, even if it's a real-time image, that's where CNNs shine. A CNN, a convolutional neural network, is best for that. It's best for looking for objects in an image. The next type of old-fashioned, old-school neural network is a recurrent neural network, or called an RNN. Now, a recurrent neural network is a special neural network adapted to work over time series data. So if you're looking, if it was 3 or 4 years ago and you're looking for stock market trading data, you would be doing that with a recurrent neural network, an RNN. So it is the most important for time series data. So data that's involving a sequence or a series. So if this stock went up today and went up this day, or this stock, let's say there is a direct relationship between the price of oranges and Tropicana stock. Okay, you would be able to use recurrent neural networks to predict the future. Okay, so that's where a recurrent neural network comes in. Now, RNNs have something that you don't see in a general feed-forward neural, which is the concept of memory, and that helps store the series or information of the previous inputs to generate the next output of the sequence. So in ordinary feed-forward neural networks are only meant for data points that are independent of each other. Okay, so again, our pixels are all independent of each other. This pixel doesn't know or actually doesn't care what the pixels next to it are. But in this case, in a recurrent neural network, where the things in the past are important to predicting the future. So suppose we have data in a sequence and that data depends on the data at the previous point. In this case, the neural network needs to be modified to incorporate the dependencies between the data points. So again, this is where the memory comes in. So we're not just training it to recognize something at a point in time, we're recognizing things that have changed over time. So now recurrent neural networks are not something that I actually worked with very often before GPTs came out, because GPTs and LLMs do an amazing job at replacing recurrent neural networks. Recurrent neural networks, as useful as they were as far as determining sequences and determining a time series, they just had a crazy amount of limitations. And the biggest limitation was how much of that memory that I just talked about does the recurrent neural network have. So if we were talking about an LLM, where we're talking about, let's say, a 30,000 token context window, you're not going to get more than a couple of hundred past series of your sequence when you're dealing with a recurrent neural network. So in the old school world, I'm just making sure I've got all my notes here. Okay, in my old school world, your 3 types of neural networks are your feed-forward neural network, which that's like your multi-layer perceptron. Your convolutional neural network, that's not just trying to determine if something is a 1 or 2 or a 0. It's trying to find out, is there a dog in this picture, or what is in this picture? Okay, that's your convolutional neural network, your CNN. Then your RNN is your neural network that does series in time. So that's your time series neural network. Now, the reason I created this video isn't necessarily because you need to know everything there is to know about a feed-forward neural network, a convolutional neural network, or a recurrent neural network, but you need to know they exist. Okay? You need to know they exist, and you also need to look at it, especially in the case of a CNN. Is the thing you're trying to do with your GPT, could that better be done with one of these other types of neural networks? So when you think of how a GPT works, and I haven't decided if I'm going to go into that level of depth And we could talk through it, but that video would be like a 3-hour video. So I'm going to question whether or not I'm going to do that in the future. But knowing what a neural network is, because a neural network is the foundation of artificial intelligence, it's just important that you know what a neural network is. So again, I think I'm going to cut it off now. The reason for creating this video it's really important that you understand the basics of neural networks, because that is the vocabulary that you're going to hear from everything that you're doing in artificial